Okay, let's jump into something. Well, pretty unexpected today.
Definitely.
You know how sometimes you're sitting in, say, a math class, looking at these really abstract ideas?
Mm-hmm. Like how things change over time.
Exactly, like derivatives.
Yeah.
Now, hold that thought and picture a farm,
Okay.
livestock cows, maybe sheep,
Mm-hmm.
and they're eating specific organic feed.
Worlds apart, you'd think.
But we stumbled upon some notes about making an interactive video for college students, actually.
And that's the link. It's fascinating. These notes explore using calculus
Calculus.
to potentially spot illness in those very animals.
So that's our mission for this deep dive.
Yeah.
Figuring out how these math tools, specifically differentiation, might actually be used for, animal health checks.
And the source material points directly at heartbeat changes.
Heartbeat changes. So how do you even get from a heartbeat, a biological thing, to calculus?
Well, the notes really focus on the derivative, the power of the derivative.
Okay, so refresh us. A derivative, basically it measures rate of
Right.
change, right?
Exactly, the rate of change. So if you're monitoring an animal's heartbeat, maybe beats per minute, maybe the gap between beats,
Uh-huh.
you get the stream of data over time.
Right. And I guess a healthy animal's heartbeat isn't perfectly flat.
No, not at all. There's always some natural variability, but the way it varies, how quickly it speeds up or slows down, that tends to follow certain kind of normal patterns.
Okay.
And the idea in these notes is that when an animal starts getting sick, maybe before you even see anything,
Yeah.
that rate of change, how the heartbeat fluctuates, can start to shift subtly.
Ah, so you're not just looking at the number, like is the heart rate high or low?
Yep.
You're looking at how fast the rate itself is changing, like acceleration.
That's a great way to put it. Acceleration or deceleration of the rhythm.
Mm-hmm.
By calculating the derivative of that heartbeat data,
Okay.
you can actually put a number on those subtle shifts in the rate of change.
And the notes suggest there are specific patterns in those derivatives.
Yes, patterns or deviations that might flag stress or sickness way earlier than just, looking at the animal.
Like a mathematical early warning system.
Precisely.
That's wow. And the source mentioned this specifically with livestock on organic feed. Why was that detail important?
Good catch. The notes seem to imply that what the animals eat can actually change their baseline physiology.
Their normal patterns.
Yeah. So the typical heartbeat variability, the normal rate of change for that specific group on that feed, might be different.
Ah, so you need to know what's normal for them.
Exactly. To know what counts as a meaningful deviation, it suggests the model needs tailoring. Diet, environment, these things matter for accuracy.
So it's not just plug-and-play calculus. It's applying it with real-world nuance, like diet,
Mm-hmm.
taking abstract rates of change from class
Uh-huh.
and using them to find hidden health clues out in a barn.
And think bigger picture. It shows how quantitative tools, math tools, can give us insights in places you wouldn't expect.
Like animal science.
Right. Spotting illness early means better animal welfare, maybe fewer interventions needed later, better farm management.
Especially relevant for specific approaches like organic farming.
It's all about using data, using derivatives, to see patterns that our eyes just can't catch.
So what's the takeaway here for you? Well, let's dive into some pretty niche project notes. Shows that concepts like derivatives aren't just for the textbook.
Far from it.
They have real practical uses, like analyzing biological signals in livestock, potentially spotting problems early, especially when you factor in things like organic feed. It's pretty strong evidence for how quantitative thinking helps.
It really pushes you to look beyond just the surface numbers, doesn't it? To see the dynamics.
Absolutely. Which leaves us, and you, with a final thought to chew on.
Hmm.
If derivatives, focusing on rate of change, can do this,
Hmm.
what about other quantitative tools? Maybe something like integration, which is about accumulation or total effect. Where else, in unexpected corners of your life or work, could these kinds of mathematical ideas reveal hidden patterns or information? What other problems are out there that math could quietly help solve if we just looked?